Answer to your names, please. Do this first. Percy.
Here.
Urani. Gilcrease. Gilcrease is here. Okay. Lackey is here. Luna Sanchez.
Here.
Macias. McKinnon. Morris.
Here.
Powers. Renfro. And Salvador. Spivey.
Here.
And we just walked in. Luna Sanchez, right? No, not Luna Sanchez.
Maria.
Urani. Okay. All right. So we're going to start our new chapter dealing with kinetics. So let me share my screen. Up here. Do this. Okay, so chemical kinetics. That's the next topic. So kinetics is that area in chemistry which deals with how fast a reaction will proceed. Now, in chemistry, there are two main things that we are concerned with when it comes to chemical reactions. The first of which is, will the reaction take place? All right. And then the second thing that we're concerned about is how fast the reaction will proceed. All right. So very often we have to measure what is known as the reaction rate, which is basically the change in the concentration of a reactant or product with time. And excuse me. Whichever you choose, reactant or product, in order to measure the reaction rate, is largely dependent on convenience, right? Is it possible to measure the rate by examining the change in the concentration of the reactants or products? And of course, that depends on the properties of the reactants and products, all right? So we're gonna see a couple of examples of that, but let's look at this hypothetical example. So let's say we have a reaction A going to B, then we can basically calculate the rate of the reaction using this equation here, where rate is equal to minus the change in concentration of A. I don't know if you guys are familiar with this symbol, this triangle, it means change, right? So this is a change in concentration of A divided by the change in time. And you'll notice there's a negative sign here. And the reason why there's a negative sign is because the reactant is changing, is decreasing, all right, in terms of its concentration, all right? Or we could look at the rate in terms of the change in concentration of B, in which case this would be the equation you would use, where rate is equal to the change in concentration of B divided by the change in time, where delta B, of course, is the change in concentration of B over that time period, all right? So that's just a simple example, which basically illustrates how you determine the rate change for either product or reactant. So you'll notice that there's a negative sign here, but there's no negative sign here. In this case, that's because B is being increased as the reaction progresses, all right? So this is just reiterating what I just said, because changing concentration of A decreases with time, then delta A would be negative. Okay, so let's look at this particular hypothetical example in more detail. 1 minute. So the black spheres represents A molecules, and the red sphere represents B molecule, right? So we're starting off with only A to begin with, and then as the time progresses, you're going to see that there's a decrease in the amount of A molecules and a corresponding increase in the amount of the B molecules, right? So if you were to plot a graph of the number of molecules versus time for both A and B, you'll see that there's a gradual decrease in the number of molecules of A, and correspondingly, there's a gradual increase in the number of molecules of B, right? And this is pretty much what you'd observe in the vast majority of cases where you have a reaction taking place, if you were to monitor the amounts of reactants or products. Okay, so again, the rate can be calculated as being equal to minus the change in concentration of A versus divided by time. And the rate, as far as B is concerned, can be expressed as the change in concentration of B over change in time, all right? Now, here's a real example, a real chemistry example of a reaction rate experiment. So here we have a reaction. This is the equation for reaction. The reaction is between bromine and formic acid. That's what this is, or methanoic acid, that's the other name for it. And it gives these products, right? Now, in this particular case, we would monitor the reaction by looking at the color of the solution, because the bromine imparts a brownish, well, orange brownish color to the solution, right? So as the reaction progresses, of course, as we can see here, as time progresses, what happens? The color of the solution becomes less and less intense until you get to a situation where it's colorless, which means that all the bromine has reacted, right? So we can actually measure the intensity, or I should say, how should I put this? Indirectly measure the concentration of bromine by monitoring the intensity of the color of the solution, right? And there's an instrument that is used known as a spectrophotometer, which basically is used to measure the intensity of a solution by looking at how much light is absorbed from it or by it when you try to pass a light beam through it. So here we have our light, and the light source must be of a particular wavelength, and that light beam is allowed to pass through the solution, and then some of it will be absorbed if the solution is colored, and then the rest will basically be detected here, and the detector will measure the level of absorbance of the light source after it has passed through the solution, right? So what this is showing you is basically what we call the absorption spectrum for bromine, right? Bromine absorbs at the maximum at 393 nanometers, right? So that's why you need this to be set at that particular wavelength so that you can accurately determine the amount of absorbance of the light by the bromine in the solution. And there's a direct relationship between the absorbance and the concentration, right? The greater the concentration of bromine, the greater will be the absorbance that you would measure directly, right? So basically the absorbance can be seen as a proxy for the concentration, all right? And this is one of those examples where, okay, you cannot conveniently determine directly the concentration of the reactant, but you can use something else as a proxy, in which case it's the absorbance that would be used, all right? So as stated here, the change in concentration of bromine would be proportional to the change in the absorption of the solution, all right? And therefore, we can get, I think we have a graph, or not graph, but data from this experiment. So basically, this is the data that's collected, right? Using, again, we're going with this reaction right here. These are the times, and these are the concentrations. These concentrations, as I said before, are not obtained directly. You have to do the absorbance measurement first, and then you calculate the absorbance or calculate the concentration based on the absorbance, right? So that's what you get as far as the data is concerned. And if you were to plot a graph of the concentration of bromine versus time, this is what you're going to get, right? And then what this person did, whoever this experimenter was, he or she determined the rate of the reaction at an instant, right? Now, at this juncture, I want to make a distinction between what is called the average rate and what is called the instantaneous rate, right? So the average rate is basically the change, it's kind of similar to what we discussed earlier. It's a change in the concentration of a reactant or product divided by the change in time. Now, in this case, since we're looking at the reactant, it would be equal to minus the change in the concentration of the bromine over time, right? So in other words, you have to choose two time intervals within which to calculate the average rate. So a more expanded way of expressing this equation would be the final concentration of bromine minus the initial concentration of bromine divided by the final time minus the initial time. And of course, again, you can't forget the negative sign here. So basically, when we're talking about the average rate, we're talking about over a particular time interval, right? Now, the instantaneous rate is different. The instantaneous rate, as stated here, is a rate for a specific instance. And the way we determine that is graphically, right? So in this particular case, what you do, and I'm quite sure you're familiar with this from your previous math experience, you choose a point. Let's say you want to find the instantaneous rate at 100 seconds, right? Then you draw a tangential line touching that point on the curve, and then you find the slope of that line, right? Rise over run, which I'm quite sure you have met before, right? And basically, once you get that calculation, that will give you the rate at that particular time. So this person, whoever he or she was, did the instantaneous rate at 100 seconds, 200 seconds, and 300 seconds, and these are their values, right? So at 100 seconds, it was 2.96 times 10 to the minus 5. At 200 seconds, the instantaneous rate is 2.09 times 10 to the minus 5. And then at 300 seconds, the instantaneous rate is 1.48 times 10 to the minus 5 m over seconds, right? So that's basically how you determine the instantaneous rate as opposed to the average rate. So just to briefly recap, the average rate is the rate measured over a particular time interval. It's the final concentration of the reactant minus the initial divided by the final time minus the initial time. The instantaneous rate is basically obtained by determining the gradient of the tangent that touches the line at that particular interval, at that particular instance, all right? So that's the difference between the instantaneous rate and the average rate. Okay. So this is just emphasizing again, it's a slope that is being determined in each case. Okay. So let's look at this in more detail. So what is shown here is the same data as I showed you previously, but this time they included another column here, which basically involves the determination of the rate as I talked about earlier, the instantaneous rate. And then what this person did was try to find a relationship between the rate and the concentration of bromine. So what they did was that they divided the rate by the concentration of bromine. And what you notice here is that there's a very close correlation of the data resulting from that, right? So basically what this is suggesting is that the rate is, in this particular reaction, directly proportional to the concentration of bromine, right? So what this means is that as the concentration is doubled, the rate will be doubled. If the concentration is tripled, the rate will be tripled, and so on and so forth. So that's a conclusion that we can come to based on this direct evidence here. And not only that, but the graph that is plotted here. This is a graph of the rate versus concentration. And again, you see what? A straight line, again, indicating the direct proportional relationship between the rate and the concentration, right? So another way of expressing this equation is rate is equal to K times the concentration of bromine, which means that K is equal to rate divided by the concentration of bromine. And that K is given a special designation. It's called the rate constant for the reaction, all right? Now, let me just say, and we're going to see this shortly, that not all reactions gives that direct linear relationship, right? We're going to see some instances where the rate will be proportional to the concentration of a particular reactant squared, for example. In some cases, believe it or not, there are instances where the concentration of a particular reactant does not affect the rate at all, right? So they're different, and the only way you can determine, whichever will happen is through experiment, like the one that we just looked at a while ago, all right? But this is just one example where the rate is directly proportional to the concentration of bromine. Okay, so that is that. This is just giving you the value, which I think is maybe the average of these, or you can get it from the slope of this line, same difference. Okay, so here's another reaction, the decomposition of hydrogen peroxide. Now in this case, this reaction produces water and oxygen, right? So basically, in this particular case, in order to monitor the reaction in terms of the rate, the best way to do this, or the most convenient way to do this, is to monitor the pressure of the oxygen, because there's a relationship between the pressure and the concentration of a gas, right? If you recall, in your general chemistry 1, the ideal gas equation, PV is equal to nRT. Well, you can rearrange this equation to get P is equal to N over V times RT. N over V is basically the concentration, right? In this case, it's oxygen gas being produced. So we can replace this with the concentration of O2, right? So therefore, by monitoring the pressure, you're effectively monitoring again the O2, which means that the pressure can be seen as a proxy for the concentration of O2, right? So basically, in this particular case, this is where the reaction is taking place. Oxygen gas is being produced, and that gas is led into the U-shaped tube, which you guys should be familiar with from your previous General Chemistry 1 manometer, which is used to measure the pressure of a gas, in this case, a gas being produced here. So basically, the way this experiment will be conducted is that you have the hydrogen peroxide here, and then you start timing, and you start watching the pressure reading here. And at each time interval, let's say every 10 seconds or so, you measure the pressure, and then you get the data of pressure and time, all right? And in so doing, you can determine the rate of the reaction and the relationship between the rate and the concentration or pressure of the gas, all right? So these are just equations that showing you the relationship between the rate of the reaction and ultimately the change in concentration of O2 over change in time, which would be equal to this right here, because concentration of O2 would be equal to P times 1 over RT. So basically, the result would be this. And basically, that gives you the relationship between the rate versus the change in pressure, right? And then the person who did this experiment got data. And basically, when you plot the pressure versus time, this is the data or the graph that you get. And again, you can find the instantaneous rate, just like I described earlier. If you want to find the instantaneous rate at, let's say, 400 minutes in this case, then basically you draw a tangent again and determine the slope, and that gives you the rate at that particular time. And that rate will be measured in millimeters mercury per minute. And you can convert that to molarity per minute if you want to, if you're required to, and so on, all right? Let me just say here that when it comes to measuring rates, or the times of reactions, I should say, they can be all over the place. You can have reactions which occur very instantaneously, like nanoseconds. And then you have reactions which literally take millions of years. So, what you'll find is that the unit of time that is used is largely for convenience. It could be nanoseconds, seconds, minutes, hours, days, years, etc. Excuse me. Okay, so that's another example. So let's look at some relationship between reaction rates and the stoichiometry of a reaction. So we're going to look at this particular hypothetical example where you have 2 moles of A reacting to form 1 mole of B, right? So obviously we know, based on, very elementary chemistry stuff, 2 moles of A disappears for each mole of B that is formed, all right? So the result of that is, if you look at the rate of the reaction, the rate of disappearance of A would be twice that of B. Or another way of stating it is that the rate of appearance of B would be half that of A, right? So we can say that rate is equal to minus half of the rate of change of A, again, minus because A is being used up, and that rate would be equal to also the change in concentration of B over T, right? So therefore, these two would be equal to each other, and that is based on the stoichiometry of the reaction. So to give a more direct or another hypothetical example, let's say we have this reaction here, where the lower case letters represents the coefficients, the uppercase letters represents the substances involved, then the relationship between these in terms of the rate of the reaction can be given as this, right? Basically, let's start off from here. The rate is equal to minus 1 over lowercase a times the change in concentration of A versus time, or with time. And then that will be equal to minus 1 over B, lowercase b, times the change in concentration of B versus or with time. And then here, 1 over C, there's no minus because C is being produced. So 1 over C times the rate of change of C equals to 1 over D times the rate of change of D, right? So this is basically how we can relate the different rates of either disappearance of reactants or appearance of products, along with the coefficients as expressed in the balanced equation, right? So for example, this question is asking for you to write the rate expression for the following reaction, all right? So they gave you the balanced equation. So what they're asking for is something similar to what I gave you right here, right? So going back to the question. So basically, you're going to start off with rate is equal to, as far as the CH4 is concerned, by the way, this is called methane. As far as the methane is concerned, the rate will be equal to minus the rate of change of methane with time, but you have to have a minus sign here. And then as far as the O2 is concerned, the next term would be equals to minus half, because of the coefficient of 2, this will be half here, times the rate of change of O2. And then on the product side, this will be equal to the change, rate of change of carbon dioxide. And then when we get to the water, because of the 2 here, this becomes half of the rate of change of H2O, all right? So basically you see the role in this expression here, where the coefficients will come into play. Basically for each of these substances, you're going to put 1 over that coefficient beside the term for the rate of change of that substance. And that's basically how that is done, all right? Any questions so far? Any questions? So, let me start you off with assignment number 2. Take one of that down. And for those of you out there in Zoom, let me, if I've not done so already, publish this right now. So let me go to assignments. Okay, so I didn't publish it, so let me do that now. And let's open up this so that we can all look at it together. Okay, so this is assignment number 2. Where's my pen? All right. So let's look at the first question. It says, when starting a reaction, the concentration of one of the reagents is 1.50 m. It says after 30 minutes, the concentration of this reagent is 0.85 m. So the question says, using these data, determine the average rate of the reaction in m per second, all right? So if you remember, I said that the average rate, which I just discussed, would be equal to, so let's say I'm just going to use A to represent the reagent. Well, let me just say this first. It's going to be equal to change in concentration of the reagent, which is, I'm going to designate as A divided by change in time. That should be minus because A is a reactant. Let me avoid confusion. This is equal to minus change in concentration of A, right? So that would be equal to minus, so what's the change in concentration of A? If you recall, I tell my students from Chem 1, whenever you see change in anything, in any chemistry question, it's always final minus the initial, right? Final value minus the initial value. So the final value in this case is 0.85 m, and the initial value is 1.50 m, all right? And that's for the change in concentration. Over the change in time. Now, basically they said 3 minutes, 3.0 minutes. So that would be the change in time, right? So that would be 3.0 minutes. That would be the change in time. However, the question is asking for the rate in what? M per second. So what do you think we need to do? We have to convert this to seconds. And we do that by 60 seconds over 1 minute multiplied by the 3.0 minutes. And then we work that out. Where's my calculator? And please do the calculation along with me because I'm subject to error. Okay, so 0.85 minus 1.5, and then I put a minus sign in front of that, then divided by 60. Okay, so the answer I got, and correct me if I'm wrong, is how many sig figs? 2 sig figs. So 3.6 times 10 to the minus 3, and the units would be m over seconds. All right? And that's how that is done. Any questions about this? Any questions? Any questions? Any questions out there in Zoom? No questions? Okay, so can I click? Oh, yes, ma'am.
0.00036.
Yeah. My calculator just automatically put it in scientific notation.
Okay.
Right. So, yeah, if you put 0.0036, yeah, that's correct, yeah. Okay, can I clear this? All right, so let me do that now. And let me do this, and let me scroll down to number 2. So number 2 gives you an equation, and it says, use the table of data shown below to calculate the average rate of the reaction, A, between 10 and 30 seconds, okay? How would you think we should do that? So let me turn on my pen function again. Okay, so they're asking for the average rate between, this for NO, okay, very important. So basically, the average rate would be equal to minus change in concentration of NO divided by change in time, all right? Okay, so how would you calculate the average rate between 10 and 30 seconds? 10, 30.
Minus 0.073.
0.73 m minus
0.110.
0.110 m divided by 30 seconds minus 10 seconds, exactly. Let's see what that gives. 0.073 minus 0.110, and then put the minus sign here, divided by, so 30 minus 10 gives you 20, so divide by 20. So according to my calculations, now in this case, I'd have to round off to 1 sig fig, so that will be equal to 2.0, I'm sorry, 2 times 10 to the minus 3, and the units here would be m over s, all right? Any questions about that one? Any questions? Okay, so do I need to do the other one? Because I mean, it's basically the same thing. The only difference is instead of this, you're going to use that along with this, right? Same idea, all right? So I leave you to do it on your own. If you have any questions about it, please feel free to contact me, all right? Okay, so let me clear this. Let me see, can we do another question? Let's see. Oh, yes, we can, all right. So this one gives you the equation for the reaction, balance equation. And it says that the rate of formation of NO2 is 4.0 times 10 to the minus 3 moles per liter per second, right? So the question is asking for the rate of disappearance of N2O5. So let me turn on. Okay, so the first thing I'm going to write down is what is given. The question says that the rate of formation of NO2, which would be the change in concentration of NO2 over time, will be equal to 4.0 times 10 to the minus 3 m per second, right? So this is what you're given in the question. Now the question is asking for the rate of disappearance. So basically of N2O5, by the way. So the rate of disappearance of N2O5 is what the question is asking for. All right? Now, if we look at the stoichiometry of the equation, you see that for every 2 moles of N2O5 that reacts, 4 moles of NO2 is produced, right? So the relationship between the rate of formation of NO2 and the rate of disappearance of N2O5 is 1/2 minus times the concentration times the rate of change of N2O5 is equal to 1/4 times the rate of change of NO2. All right? Now this here, we already know, is equal to 4.0 times 10 to the minus 3 m over s, right? So we know that minus half of the rate of change of N2O5 is equal to 1/4 times 4.0 times 10 to the minus 3. And we can simplify this to give you 1.0 times 10 to the minus 3. So therefore, we can say that the rate of N2O5 change will be equal to minus 2 times 1.0 times 10 to the minus 3 m over s, m over s. So that works out to be equal to minus 2.0 times 10 to the minus 3 m over s. And therefore, we can say, because of how the question is worded, the question is asking for the rate of disappearance. We can therefore say that, continuing down here, rate of disappearance of N2O5 is equal to 2.0 times 10 to the minus 3 m over s. And that's how that is done. All right, any questions? Any questions? Is it okay for me to clear this, or are you still writing?
Oh, I'm still writing.
In the meantime, let me see who came in late. Okay, so Macias, Renfro, let me see. Oh, Renfro is here, okay. And Salvador. Okay, I don't see Salvador. Okay, can I clear some?
Okay.
Okay, so the next question. Let me make it smaller so I can see what's above. Next question is calculate the rate of appearance of O2. So what this question is asking for is the change in the concentration of O2 divided by change in time. So that's what the question is asking for, the rate of appearance of O2. Now, if we look at the relationship stoichiometrically between NO2 and O2, it's a 4-to-1 ratio, right? So basically, we can say that the change in concentration of, or the rate of formation of O2 will be equal to 1/4 times the rate of formation of NO2, right? So basically what this is saying is that NO2 will be formed 4 times faster than O2. So basically all we have to do is plug the numbers in because we know what this is already. That is equal to this right here. So we're gonna have 1/4 multiplied by 4.0 times 10 to the minus 3 m over s, and that's it, 1.0 times 10 to the minus 3 m over s. That's how that is done. Right? Any questions about this one? Yes, sir.
What's the difference between the rate of appearance and rate of disappearance, like formula wise?
Well, basically, okay, so let me say this first. Whenever you see something like this right here, this means change, change in the concentration of, in that case, oxygen versus time, right? Or another way of expressing it would be rate of change of concentration of O2, right? Now, the rate can be either negative or positive. See what I'm saying?
Yeah.
If rate is positive, that means that the substance is being formed. If the rate is negative, that means that the substance is being used up. So when we say that, like, what was the answer for the first one? Was it 2.0 times 10 to the minus 3?
Yeah.
Right. So in that case, the question was asking for the rate of disappearance of N2O5, right? So the final answer would say the rate of disappearance of N2O5 is 2.0 times 10 to the minus 3, right? That is the same thing as saying the change in the concentration of N2O5 is minus 2.0 times 10 to the minus 3. You see what I'm saying?
Yeah.
So that's basically where that slight difference appears.
All right, thank you.
Yeah. Okay, let me clear this. And let me scroll down to see if there are any more questions we can do at this juncture. Okay, no, we can't do that one yet. All right, so let me go back to the PowerPoint. And let's talk about now what is known as the rate law of a reaction, right? So the rate law of a reaction is basically an equation which describes the relationship between the rate of a reaction to the rate constant and the concentration of the reactants, which will be raised to certain powers or exponents. All right, so again, going back to our hypothetical example reaction, the rate law for this reaction can be written as rate is equal to K times concentration of A raised to the X times concentration of B raised to the Y, all right? Now, first thing I want you to notice is that the rate law can only be written in terms of the concentration of the reactants, right? The products will not appear in the rate law, all right? So that's the first thing I'm going to say here in terms of the concentration terms here, right? Some other terminology that applies here. So if you are given this rate law here, or if you determine this rate law, then we can say that the reaction is X order with respect to A and Y order with respect to B, all right? And overall order would be the sum of the two orders, right? X and Y, all right? So those are just some terms that you need to be aware of, all right? Oh, and let me just say this. I don't at this point, let me say something here. Oh, okay, I won't say it yet because the point is made later on. All right. So that's basically your first introduction to this whole idea of rate laws, right? So basically the rate law is given in or determined in this way, right? Of course, there are variations depending on, especially whether or not you have values of X and Y involved, all right? So here's an example. So somebody did this experiment, and what they did was that they have, okay, so this is a reaction here, and then they basically did some rate measurements, initial rate measurements, based on the concentration of the reactant, right? And so when the concentrations of fluorine and ClO2 are these two values, this is the initial rate, and then what this person did was quadruple the concentration of ClO2, and the rate changes as a result. And then this person in the third run doubled the initial concentration of fluorine, right, while the concentration of ClO2 remains the same, and we get a value for the concentration here. So basically what they're doing is adjusting the concentration of one reactant, leave the other reactant constant, and see what effect that has on the rate of the reaction, right? So we're going to write a generalized rate law for the reaction, which is rate is equal to the constant times concentration of F2 raised to the X times the concentration of ClO2 raised to the Y. So this is how you solve a problem. And this is the way I want to see you guys solve it. All right? And there's a reason why I'm stressing this, because In some cases, this is the only way to solve it, right? So what I'm gonna do is, I'm going to write down the rate law, but input the data that is given, right? So this is for the first run, right? Rate, which is 1.2 times 10 to the minus 3 m over s is equal to k, we don't know what that is, times the concentration of F2, which is 0.10 raised to the x, m raised to the x, times the concentration of ClO2, which is 0.010 m raised to the y, right? Then for the second run, the rate is equal to 4.8 times 10 to the minus 3 m over s equals to k, again, we don't know what k is, times the concentration of fluorine, which is 0.10 m raised to the x, times the concentration of ClO2, 0.040 m raised to the y, all right? So the next step is to divide the top line by the bottom line and cancel out those items which can be canceled out, like the 10 to the minus 3 here and here, the units here, the k's here. This will cancel out with this. So basically you're going to be left with 1.2 over 4.8 equals to 0.010. Oh, by the way, the m's will cancel out here and here as well. So you're going to get 0.010 divided by 0.040, right? And all of this will be raised to the y. So the 1.2 divided by 4.8, you can see that is equal to 1 over 4. This here, you're going to see that is equal to 1 over 4 raised to the y power. So what does that tell you about y? What is y equal to? Anybody? Should be simple enough. If 1 over 4 is equal to 1 over 4 raised to the y power, y is equal to what? Exactly. So therefore, we know that the y here would be equal to 1, right? Okay, now I need to clear this in order to move on. So let me know when you're through writing all this down. Finished? All right, let me clear this. So the next thing I'm going to do now is compare this line to the third line, the third run, all right? And if you compare these two, you'll notice that the concentration of ClO2 is constant, while the concentration of F2 is double. So I'm going to start off with 1.2 times 10 to the minus 3 m over s. That is equal to k times the concentration of fluorine, which is 0.10 m raised to the x. We already know what x is already. It's 1, but it doesn't matter. So I'll just put 1 here. And then for the ClO2 is 0.010 m raised to the y. This is what we're trying to find. We're trying to find y. And then down here, I'm going to put 2.4 times 10 to the minus 3 m over s is equal to k times 0.20 m. Oh, my bad. This is x. Y is equal to 1. That's what we determined earlier. So let me, well, I'm going to leave y there. It doesn't make a difference. You'll see y shortly. 0.010 m raised to the y, all right? Again, you divide the top line by the bottom line. So this will cancel out, so it doesn't matter what y is in this case. The m's will cancel out here and here, the k's will cancel out here and here, m over s will cancel out here and here, 10 to the minus 3 will cancel out there and there. So this will simplify to 1.2 divided by 2.4, and that would be equal to 0.10 divided by 0.20 raised to the x. So 1.2 over 2.4 is equal to a half, and that will be equal to 0.10 divided by 0.20, which is also a half, raised to the x. So therefore, x is equal to, again, 1, right? So now we have determined that x is equal to 1, and y is equal to 1, right? So we say that the reaction is first order with respect to fluorine, and first order with respect to ClO2, and second order overall. So we can say here that the overall order is equal to 1 plus 1 equals to 2. All right? And that's basically how we determine the orders of the reaction if you're given data like this. All right? Okay, any questions about this? Any questions? Questions? Okay, one more thing I want to talk about with this question is that sometimes you may be asked to determine the rate constant, the K value, right? So let me show you how to do that. Let me clear this first. So to get the K value, we go back to this equation right here. In fact, we go back to the equation where rate is equal to K times the concentration of F2 times the concentration of ClO2, all right? So we know what the order of the reactions are with respect to fluorine and ClO2, so we know that's 1 there, 1 there. To find K, we simply rearrange the equation algebraically to get rate is equal to, K is equal to rate divided by concentration of fluorine times the concentration of ClO2. And then all we have to do from here is choose any one of these 3 sets of data to plug in their respective values into this equation to get K. It doesn't matter which one, right? So I'm just going to use the first set of data, right? Rate is equal to 1.2 times 10 to the minus 3 m over s divided by, for fluorine, that's 0.10 m multiplied by, for ClO2, 0.010 m. And let's see what that gives. 1.2 times 10 to the minus 3 divided by 0.1 divided by 0.01 equals. Okay, so according to my calculations, this works out to be equal to 1.2. And in terms of the units, this will cancel out with that. So you're going to end up with m to the minus 1 seconds to the minus 1. And that's basically how that is done. All right? Any questions about this? And as I said before, you could use any one of these sets of data and plug them into this equation, you get the same result. It doesn't matter which one you use. All right? Okay, any questions about this one? Any questions? All right, so let me here it is. And let me scroll down. Okay, so that's that. Okay, some things about rate laws that you need to be aware of. The first of which is that rate laws can only be determined by experiment, right? You cannot look at an equation and tell what the rate law is. That's a very common misconception for people meeting this topic for the first time. The only way you can determine the rate law is by getting experimental data like the ones that we just saw, and we work it just like we just did, all right? That's the first thing. The second thing is, and I made this point earlier, the reaction order is always defined in terms of reactants and not products, right? So that's why the rate laws only contain terms for reactants and not the products of the reaction, all right? Third point here is, and again, this is a common error that students tend to make when they meet this for the first time, the reaction order is not in any way related to the stoichiometric coefficient of the reactants in the balanced equation. All right? So for example, in this case here, remember we determined that y is equal to 1, right? But the coefficient of that same substance is 2, right? So there's no necessary correlation between the coefficient and the order of the reaction for that substance. Now, there are some instances where they're equal, but that is purely by coincidence, right? So the only way you can determine the orders of the reaction is by way of the type of calculations we just did if you're given the data, all right? So those are 3 important things you need to be aware of when it comes to rate laws. And this is just basically stressing what I just said in the example of the reaction between fluorine and ClO2, right? Clearly, there's no similarity between the coefficient of ClO2 and its order in the rate law. All right, so here's another example here. Now, based on what we have done, you should be able to walk me through the solution to this problem. So let's hear what you have to say. Hold on, let me see here. So they gave you the equation for the reaction, and they gave you the experimental data. So the first thing, let me start you guys off. The first thing I'd write down is the general rate law. Rate is equal to K times concentration of S2O8, 2 minus raised to the X, times concentration of I minus raised to the Y. All right? Okay. So how would you move on from there? What would be the first step? You can look back at what we did before in order to help you.
Writing down the given stuff for the 1 and 2.
Okay, let's do that. So for 1, what would you write down?
2.2 times 10 to the negative 4th is equal to K.
Mm-hmm.
0.08 to the X
Mm-hmm.
times 0.034 to the Y.
Mm-hmm.
Two would be equal to 1.1 times 10 to the negative 4 equal to K 0.08 to the X and times 0.017 to the Y.
Okay, very good. And then what?
0.08 is gonna cancel out.
Okay, so we're dividing, right?
Divide, yeah.
Let's cancel out stuff that can be canceled out. Well, this will cancel out with that. And this will cancel out with that. So what will you be left with? You'll be left with equals to
0.034 divided by 0.017 to the Y.
okay, very good. So the 2.2 divided by 1 will be equal to 2. And the 0.034 divided by 0.017 would be equal to 2 as well, raised to the Y. So Y is equal to
1.
1. Okay. So we know that Y is equal to 1. All right. Okay, let me know when you're finished with this so I can erase it. Yes? No? Yes, ma'am.
0.034.
You mean here?
Oh, okay.
That's where this comes from. Finished? All right, let me erase down here since I'm gonna need a space. Okay, what will be the next step? Now that we have determined what y is, what would be the next step?
The results from experiment 2 and 3.
Okay, let's see, experiment 2 and 3. Yes, I would do that too because the concentration of I minus will remain the same and the concentration of S2O8, 2 minus, has doubled. So for 2, what I'm going to write down here? For experiment 2, 1.1 times 10 to the minus 4 m over s equals to what?
0.08.
Well, what goes before that?
Okay. So
K times 0.08 m raised to the x times 0.017 m raised to the y. And then for 3, what am I going to write down for 3?
2.2 times
2.2 times 10 to the minus 4 m over s is equal to k times 0.16 m raised to the x times 0.017 m raised to the y. All right? This will cancel out with that. The k's will cancel out. The m's will cancel out. This will cancel out. This will cancel out. So you'll be left with 1.1 times, 1.1 divided by 2.2. Erase this here to avoid confusion. And then that would be equal to 0.08 over 0.16. So that would be equal to 1 over 2 equals to 1 over 2 raised to the, oh, this should be raised to the x, by the way, raised to the x. So again, x is equal to 1, right? Okay, so the rate law is rate is equal to K times concentration of S2O8, 2 minus, times the concentration of I minus, and that's it. So this would be the rate law that the question is asking for, all right? Now, the question is also asking for you to calculate the rate constant. And we did an example of that in the last example, right? So how would you determine that? How would you determine K?
is the rate over the concentration of S2O8 times the concentration of
I minus. All right, so is it okay for me to erase down here? All right, so let me do that. Okay, so as she correctly said, K is equal to rate divided by concentration of S2O8, 2 minus times the concentration of I minus. And then what do we do with that? Anybody?
We can plug in any of the rows.
Any sets of data that would be plugged, that you can plug in here. I'm just going to choose the first one. So 2.2 times 10 to the minus 4 m over s divided by 0.08 m times 0.034 m. So let's see what that gives. 2.2 times 10 to the minus 4 divided by 0.08 divided by 0.034. And this gives 8.1, according to my calculations, 8.1 times 10 to the minus 2. And this will cancel out with that. So the units will be m to the minus 1, s to the minus 1. So that's how that is done. All right? Any questions about this one? Any questions? Any questions? All right, still writing? Mhm.
Good, I can see how you get M-1, but how do you get S-1?
Oh, because you're talking about the units, right? Because of the M down here. So that's one over M, which is M to the minus one.
But what about the S? What about the S?
Well, you have one over S here.
Oh.
So that's S to the minus one. So that's why it's the final units will be M to the minus one, S to the minus one. Okay, let me clear this. This, and let's see what's next. Let me just check something here, in the assignment. Okay, so based on what we have covered, you would not be able to do number 4. Oh, I remember, shoot, I think. Oh, okay. Unfortunately, the questions are not arranged in the order that I would like. But anyway, so based on what we have done, you should be able to do number 12, which is on page 10 of the assignment. Right? So I'm going to leave that for you to do at home. Again, if you have any problems, please let me know, and I'm more than willing to help you with that. That's number 12 and also number 13. Right? So I want you to do those on your own, number 12, numbers 12 and 13. All right? Okay, I think I'm going to stop here because I don't want to start this next topic and stop in the middle of it. So that's it for today, folks. Before you leave, I just want to, I haven't had the chance to post it in the announcement yet, but I'm going to do so later on today. So the STEM Club, I don't know if you guys have heard about the STEM Club. We are hosting, I'm the faculty sponsor for the STEM Club. STEM, of course, stands for Science, Technology, Engineering, and Math. So we're hosting an event where we're introducing, well, somebody will be coming to talk to the group about STEM careers, the type of careers out there that you might find interesting. And that event will be on Wednesday, the 5th of February. So not next week Wednesday, but the Wednesday following, right? It will be held over there in building 2, the common area right there. So there'll be 2 speakers, one from the Talent Center. He's a person who will be basically giving you an overview of the different STEM careers that one can choose. And then another person will be coming from a company known as the Institute of Human and Machine Cognition, right? It's a facility, well, they have an office here in Ocala, but their major research facility is in Pensacola. And she'll be talking about internship opportunities at that organization, all right? And they're looking for students from colleges like ours. So if you're interested in STEM careers, then you're invited to come to that event. All right, I'm going to post I just got the flyer today, this morning before I came to class. So I'm going to post it in Canvas so that you guys can look at it and remind yourself of when that event will be so that you can attend. All right, that's it, folks. I'll see you guys, well, some of you in the lab. Rest of you next week. Yeah, next week. Those of you there in